Okay, so we actually keep this term to be the same. As what we did in finite volume, we move the time derivative out of this integral, because when we have a time derivative and a spatial integral, as long as the two endpoints of the spatial integral doesn't change over time, we can just pull the time derivative out of the spatial integral. So that is equal to, now is the time to apply our integration by parts. So we have the boundary term, and the boundary term, since we have a test function, let's enforce that to be differentiable with v0 equal to v1 equal to 0, right? Okay, the same kind of a compatible boundary condition as the original differential equation. So with this, the boundary term which has a v in it actually disappears. So we are left with minus kappa. Again, kappa being a constant can be pulled out of the integral. Integration from 0 to 1. One derivative is applied to v, while one derivative is removed from u. Okay, plus the third term is kept. So this is my weak form. And now we can suppose that u being a piecewise linear and constant function and continuous function, right? Because now we no longer have second derivative of u. We only have first derivative of u, which exists, right, almost everywhere. All right. Actually, du dx is now a piecewise constant function, which makes our job quite easy. All right, now what's the next step? Up to now, all our manipulations are actually exact. We haven't ever made any approximations up to this point yet, right? Everything we have done are exact and continuous and mathematically rigorous. But the next step involves approximation, as in all the numerical methods we have studied. In finite difference, we directly make approximations, right, to the differential operators. In finite volume, we have to approximate the flux as a function of the volume averages. In finite elements, we have to approximate by restricting the possible space that my solution u can live in. We also restrict the v, instead of being any function, we restrict v to be within a similar class of functions as we allow the solution u to be in. Okay, here particularly, I'm going to say my u can only be a linear combination. I goes from 1 to n minus 1 in this case, because we have fixed our boundary conditions. So u actually has to be 0 here and here. Ui times phi x. And phi x are this kind of a piecewise linear and continuous functions that are only non-zero at one of the grid points, right? So this is the first head function. Second head function, it has to be 0 for all but one grid points. And at that one grid point, the value is what? It's 1, right? So this is we call the nodal basis functions that are very convenient, as you've seen last time when we formulate the matrix, right? The sparsity of the matrix are a direct result of the features of this nodal basis function. I mean, actually, you are actually free to choose any other basis functions, right? So you can choose functions that are actually, as long as they are linearly independent, you can choose any function to use for linear representation of the unknown u. But this kind of basis functions gives you very nice matrices that are very easy to construct, as we've seen last time. So we ended up sticking to them. Okay, so we represent U to be that, and V can be equal to phi1, phi2, etc. phi n minus 1. So by choosing the n minus 1 different V's, we get n minus 1 different equations. And U is always represented as the linear combination of the same n minus 1 unknowns, right? So we get n minus 1 equations for solving these n minus 1 unknowns. The only difference between what we have here and what we got before is that these n minus 1 equations are no longer just the simple linear equations. We no longer get ax equal to b. What we get is n minus 1 coupled ordinary differential equations, because now we have this time derivative. All right. Okay, so let's see how we get that. And one thing you're going to see is the special feature of finite element. The left-hand side is not just going to be dui dt. So let's proceed. Now we plug this in. We have ddt of integration, again 0 to 1. Now let's say just we have this, we call this phi j. J goes from 1 to n minus 1. Then the v is going to be phi j. Okay, u is going to be summation of I goes from 1 to n minus 1, ui phi I dx. That's my left-hand side. My right-hand side is going to be something we pretty much already did previously. So dv dx becomes d phi j dx, du dx becomes a summation of ui d phi I dx, and again I goes from 1 to n minus 1 dx. The last term, which is just the v times f, becomes phi j times f. All right.